Hi folks, I was watching Edge Precision's YouTube channel. Awesome channel, really sharp guy and a really good machinist, and he pulled out a tool called a Shallow-Test Gauge. And as soon as I saw it, I thought, oh my gosh, that would be super handy to have. It's a tool that will allow you to measure a variety of dimensions very accurately, both internal and external. So I found them online and I saw the price. I thought, you know what, this looks like a really fun thing where we can make our own and maybe even add a few improvements to the design. I was also talking to Tom Lipton about it, and he pointed me to one of his Instagram posts from a few years back where he did the same thing. He had to measure some really small dovetail features on some of his work at Lawrence Berkeley Lab, and he made this jig here. So super cool design. I modeled up my own version, largely inspired by the SPI version, with two big differences. The first is that the SPI version uses pinholes so that you can make your coarse adjustments of your diameter. We're going to swap that out with a slider mechanism and a set screw that will give us a little bit more fine resolution in the size that we want to measure. And then I want to change the mechanism that holds the dial test indicator to something like this. I'm not sure I'm done just yet, but this will allow us to do two things. One, we can make use of a parallel flexure for our fine adjust, and we should be able to use these two parts here along with a homemade differential screw that should allow us to easily dial in very small measurements like 10,000ths of an inch. In this video, I want to start with this finger part right here. And we're going to make this out of a chunk of 4140 and a lot of really good cam tips in this video. We've got our coordinate system set on the top center of our stock. You'll notice I've got a lot of extra stock. That's just because it was the piece of scrap I had laying around. It can actually be really helpful to use either 2D or 3D adaptive to face off apart and get that sort of dynamic tool path, especially here because we're just using a 1/4 inch end mill. The other thing is I originally programmed all three of these 3D adaptives as one 3D adaptive. That's the beauty of 3D adaptive, is it's intelligent enough to do that in one operation. But it ends up I wanted slightly different settings at each level. It's also the first time I've used the Lakeshore Fireplug rougher end mill. I've heard really good things about it, and I was excited to see how it did on the Tormach. My general go-to on the Tormach with steel is to use 1/4 inch tools because I find it's easier to get a sweet spot and you can run them at equal if not higher material removal rates without breaking more expensive, larger diameter tools. We're running this at 500 surface feet and 2.5 thou feet per tooth. That's about 7,700 RPMs and 76 inches a minute, 0.03 optimal load and 0.35 inch step down. On the 3D adaptive that we're using as a facing op under heights, I've left 5,000ths on the top. We'll then come back with the parallel toolpath and clean up that face. Here I'm making use of the patch environment. So I hopped into patch, create, offset, click our surface, click OK, which creates that patch on the surface of this part, and it shows up as a body. And the icon, instead of looking like a marshmallow, looks like this little red open thing. If I hide our body, you can now see our patch surface. Go to Modify, Extend, hold down the Control key. That lets us click both the left edge and the right edge so we can extend them at one time. And you can extend them whatever distance needed. Click OK. And if I toggle the body back on, just to give you a visual idea of what that patch surface looks like. So what a patch is, we've got a card here to the other NYC CNC videos on it, but a patch creates a thickless skin. So it has zero thickness to it. It's just a shape. Under Parallel, Geometry, we've selected that patch as the machining boundary chain. And then if I turn my part visibility back on, I turn the patch off, we've said touch surfaces and selected that face. What that does is it gives us a really nice tool path that extends on both the left and the right side of this part. Next up, 3D adaptive, exact same settings, except this time no stock to leave. We're allowing the bottom height to be the surface of our part. I want to get that material roughed out and sort of surface this bevel in here. And we're then using the 3D contour operation to come in with that same end mill, and we can just walk up that face. It's leaving some stair steps. We could make those finer if we needed to. They're currently set at 20,000ths of an inch via this maximum step down. But I knew I'd have a chance to look at them while the part was still set up, so I could make them finer if needed, and they worked out fine in the end. For my bottom 3D adaptive, I wanted to actually run that toolpath below the bottom of the part. So under heights, we have model bottom minus 30 thousandths of an inch. This lets me run our cleanup tool slightly above that, in this case just 1/1000th of an inch higher. That means the face of that tool or the bottom of that tool isn't contacting any material. And more importantly, when we go to flip that part, we'll have already machined past this edge, which makes it easier to avoid burrs. I was really happy with how the Fireplug worked. Tool life seemed great. As you would expect with a roughing tool, it's making really fine chips, which just makes it easy for chip evacuation. And normally I would choke up on a tool as much as possible. Here I needed the additional stick out for that part height. But I did an offline test to make sure we were okay with that additional stick out, and it worked great. And it's worth noting that you're still better off to stick out a short, stubby tool than you are to use a tool with a longer flute length, because that solid core is stiffer than having the alternative, which is flutes. After our roughing is done, coming back to do those cleanup passes, the first one, I'm making use of tangential extension. So under geometry, I've got a 1/4 inch. So you'll notice that I've only selected the blue line, but when we click OK, you can see the toolpath extends a 1/4 inch on left and right. Again, just to give a nice smooth lead in, lead out. We are running that at 1/1000th of an inch higher to avoid any sort of a witness mark or tool mark on the floor of our part. If you're wondering what we click to get this blue line, Fusion allows you to pick contours along different Z-planes or Z heights, and it collapses or projects them down for that toolpath. So in this case, I'm holding down the Alt key, click that first contour, and then instead of holding down Alt and clicking the next one, I want to left click that, release up. I'll leave it set here to the open contour. I'll just come over, click once on that. Those two selections are now shown in that light blue. Click the green plus, and you'll notice it projects that down. And again, that combined with the tangential extension gives me the toolpath I want here. Next up, a cleanup pass around a portion of the outside profile. Another similar trick on selecting geometry here. I'm going to click once on that fillet and let up. I'll left click again, let up, and change it to be an open contour. And all that we've got selected right now is the fillet. I'm going to rotate, orbit over, select this right here, click once. Now, it selected the correct final geometry, but it went the wrong way. So if I just hover my mouse over this way and click once, change the direction, and click the green plus, you've got that toolpath. Looks cumbersome. It's actually pretty quick once you get the hang of it. Using a little bit of a hacky way to clean up this inside wall here, really my fault in the design. I didn't give myself an easy way to get an end mill right there in the corner. Won't matter from the functionality, but something I should have thought of. If we use a regular 2D contour, we're actually going to crash into our part as we machine through it. Here we're plunging down, and then as we start our linking move through that part right there, if we look from the top-down viewpoint, we're going to machine right through our part. That's the downside of anything in the 2D contour drop-down list, is that it goes where you tell it to. I have told Fusion, I want you to take a 1/4 inch end mill and machine that blue contour, so it will do it. It will not complain. What I did to fix that is I used separate tangential extension distances. So the exit is the easy one, 0.2 inches beyond the toolpath. That just gives us a 0.2 inch extension here. I used a negative tangential on the lead in to control so that that very first portion of that material that it machines were still staying off that sidewall. I just experimented with a few values and ended up with negative 71 thousandths of an inch. Just be careful when we flip to clean up the other edge, you have to switch your tangential extension distances, because now the lead in is the positive number and the exit is the negative number. Finally, some very light edge break chamfers. And I forgot to do one thing on this part, which comes to bite me in Op 2. Any guesses what that was? Drilling with a number 58 drill, 125 surface feet, 3 thou per rev, drilled great. Before I take the part out, I just like to double check my chamfers, make sure they feel good. Check my parallel op, see if I want to do any more work on that, make sure my holes went deep enough. It's easy to fix it now because I maintain the coordinate system. As soon as I pull it out, I'd have to pick up the edge, and you just risk having minor variations, especially when it comes to detailed chamfers. Feels good though, I like it. Anybody guess what I forgot to do in Op 1? I forgot to clean up this face, which was going to be my datum for op2, but no big deal, we can work around it. The problem that we have now is that common fractional parallels don't give me that right height to avoid clamping on the unmachined portion, so we'll use a gauge block to lift that part slightly off the hard jaws, which will still let us clamp a sufficient amount of the part, and it will keep the part perpendicular to the spindle. To find our Z0, our coordinate system in Fusion is based off of this face, but I can't get to that face right now. So we find the 0 of our hard jaw, we set that to 0, but I used a 50 thousandths of an inch gauge block to lift that part up. So I'm going to jog up 50 thousandths in Path Pilot. So I'm now coplanar with this face, because again, that face would have been resting on the hard jaws had it not been for that 50 thou shim. And I know these two faces are 0.3125 inches apart, so I'll enter positive 0.3125 in my Z DRO. Quick sanity check to make sure I did my Z height correctly. I brought the tool down positive 10 thousandths of an inch, holding a gauge block up against this face. And that's not going to tell me if I'm perfect within a few thousandths of an inch, but it is going to tell me I didn't transpose a number or miss a whole decimal place or have some other large amount of error that would cause a crash. Using a 3D adaptive to face that part off, I would not use a tool like the Superfly here because there's too much unsupported material between this U-shaped area. So a 3D adaptive helps to make sure we don't tear that part out or damage the tool. And then a quick parallel tool path, again, just to clean up that bottom face. I just realized that my part isn't sitting up high enough in the vise to sufficiently machine down to this face. Switch to a 0.12 inch gauge block. We had to change our coordinate system anyways because the first op on our backside was just to clean off our hat top. That exposes good clean machined geometry that'll let us do our op 2B. I wouldn't have had this problem if I'd remembered in the first op to finish machining that backside, but not a huge deal. So we'll now find the center of these two faces as well as this edge here to give us an accurate coordinate system, and that's going to let us come in, do our adaptive machining on this section here, our cleanup passes, and a final edge break chamfer. Next week, we're going to machine a number of the other parts for this, including this piece of 4140 that we're calling the beam, which itself is a modular part of this build, so we can swap it out for various different lengths over time as needed, as well as this slider piece. And then in week 3, we're going to machine the differential screw and this parallel flexure. Hope you folks learned something. Hope you enjoyed. Take care. See you soon.